Now this example gives us almost the same span beam, but the load is much different. Okay, so here we have 75 kilonewton factored load, okay, with the design load. This is the design load, so everything is here given, so we don't need to calculate the weight of the beam here. Already it is the design load. Okay, now we are asked to design this beam for shear. So the flexure design, everything is similar to what we did in the previous example. Now let's continue. In the design of shear for beam, you need to follow these steps. Okay, what does this step say? It says that there you have to calculate the shear design, okay, or the design shear, VED. This is a shear that's calculated at D distance, at effective D distance from the face of the support, or maybe the column, maybe the wall. Now then, you will determine the VRDC. This is the section capacity without stirrups. If this VRDC is greater than VED, it means that stirrups are not required. However, minimum stirrups will be provided. However, if this is smaller than this one, you need to go to the other calculations. That is, you have to calculate the section capacity that is governed by the compression of the stirrups, VRD max, and so on. Now let's continue with this one. How do we determine VRDC? It is these two formulas. You have to do this calculation and you have to compare it with this one. This calculation, this part must be greater than or equal to this one. So the maximum of the two will be taken as VRDC. Now, if VRDC is greater than VED, we said that minimum stirrups will be provided. If not, we have to go and calculate the stirrups. To do that, we have to go and determine the VRD max at theta 22. If it's okay, fine. If not, we have to try another theta. Theta vary from 22 degrees to 45 degrees for VRD max, okay? Now, once we calculate this VRD max at 22, how do you calculate VRD max? It is given by this formula, alpha times BZ times V times F. With this, I have to check whether VRD max is greater than VED. If VRD max is greater than VED, it means that our assumption theta 22 is okay. So you need to go to calculating the reinforcement. If not, we have to try it with 45. If it is greater than or less than, it matters, okay? So if it is greater than VED, if it is less than, if VRD max is less than VED, okay? If it's less than VED, you have to revise the section. If this is less than this, it means this is greater than this, okay? So you have to revise the section because this element is gonna fail, okay? Because at maximum, it cannot go beyond 45 degrees, okay? If VRD max is greater than VED, when you calculate it, now you have to calculate the actual theta, because theta vary from 22 to 45. It may be 25, it may be 30, 35, whatever, okay? So you need to provide this. It must be less than or equal to 45 degrees. Now, once we do that, we go to calculation of the stirrups with this formula, and we need to check whether minimum requirement is satisfied or not. Once we satisfy the minimum requirement, again we need to check whether maximum spacing is satisfied or not. Now this is the full step for the shear design. So for this example, this beam depth is given 500 by 300, okay, for this example. Now the summary of what we have been talking about in the steps are this. So whenever you are designing a beam, you need to perform first these steps, okay? You have to design for flexure first. Once you find the reinforcement for flexure, the data here, the depth, the beam, the width, the reinforcement that is calculated here will be used in the calculation of the shear, okay? So in the shear calculation, we have these 6 steps, main steps, or the chart that you saw in the previous slide can be summarized here. Then we will follow these steps one by one. Okay, now with the design for flexure, okay? Now for us, let's assume, or let's start with the concrete grade. So I have taken this C25 by 30 and the longitudinal steel reinforcement S460, and for the stirrup 400. Assume the bar diameter 24 and the stirrups 8. Now with this, I have to calculate the design strength for the concrete. It is this much. For the steel, FYK is 460. It is 400, and for FYK 400, it is 347. So for the stirrups, I will use this. For the main bar, I will use this, and the overall concrete grade will be the design strength will be 14.17 or 167, almost 17. Okay, now these are given here. Okay, so the material and the section geometry is here. So from this, I will determine the effective depth, that is this, and I get 450 millimeters. Okay, now I will calculate the longitudinal reinforcement. So I need to analyze. So from the analysis, the maximum moment, it is simply supported WL square over 8. It gives me this much moment. With this, the shear force diagram is this one, and the bending moment is the maximum is this one. So we will design for the maximum, and for shear, I have this much at the support and this much at the support. Sometimes you may see this diagram is flipped. Okay, this diagram is flipped. So depending on what you are following, okay, the convention that you are following, this may be sometimes downward and upward. Okay, depending on the convention that you are following. However, the values is very important here, 225. Okay, now after design calculations, okay, this much for this much moment, there is for the tension part 524 is required, and in the compression zone it says that we need 514 bars. So the concrete by itself could not sustain. So in the compression zone, the concrete was weak, and the reinforcement, additional reinforcement is needed here. Okay, so this is in the compression zone, this is in the tension zone. Now for the design shear, we said that we will follow those 6 steps. Let's start with the first one. Okay, now here we have the maximum shear. We need to determine the design shear. Okay, the design shear. We say that the design shear will be the shear that is found at d distance from the face of the support. This is my support. So from this phase, I need to go d distance and calculate the design shear at some location here. So here, this is given in this article in both the Eurocode as well as the Ethiopian code. Okay, now it says in the Ethiopian code, for members that are subjected to predominantly to the uniformly distributed load, the design shear shall be checked at a distance d from the face of the support. However, there is additional verification that will be required. In addition, it should be verified that the shear at the support does not exceed VRD max. So we need to check this, okay, always. Now, this will be sure, okay, this will be the case. At the support means here at the support, at the center of the support, okay. However, if you have a column here, this column may have a length, a height or a length at the bottom or maybe at the top. So when the beam comes here with a depth of 500, once it passes this phase, it will have a different depth that's very large, okay, because it's a column here. So we need to check if there is a column support here or a wall. You need to check it at the phase of this beam, okay, at the phase of the support, if there is a column or a wall here. If the beam is simply going from one side to the other side, you may check it somewhere maybe inside here, okay, at the center maybe. So here for this example, I will check here at the face of the support, okay. Well, let's go. Now the design shear will be at a distance d, that is 180. You can calculate this with the similarity of triangles. You know this height, the distance from here up to here is 3 meters because the total is 6 meters. So this is 225 by 3 will be equal to VED divided by the distance from here up to here, because we know here C over 2 means C is the column dimension. So C over 2 means 300 divided by 2, it is 150 millimeter or 0.15 meter. D is calculated to be 0.45 meter. So we can calculate the remaining part. So with this similarity of triangle, you can easily calculate it. Okay, again the shear at the support will be similarly calculated, and you can get this support shear 213.75 kilonewton. Once we get that, we can go to the second part. Okay, that is determine the capacity of the section without stirrups. If the VRDC is greater than this one, so no more calculations is needed, and we will go directly provide a minimum reinforcement. Or you need to maybe minimize the cross section, maybe revise the whole section from the beginning. Okay, however, let's continue and check it. VRDC is given by this formula. This should be checked and to be greater than or equal to this part. Now CRDC is given and C is given. Everything is calculated with these formulas, given formulas. CRDC is given by these formulas. 0.18 divided by this. This is the factor of safety. So we get this. K means this one is found by this depth 200 divided by depth and radical plus 1. You get this. Now this is the ratio, okay, of the reinforcement. AS divided by BWD. Now, since here the reinforcement, we knew that 5 phi 24 is required at the bottom and 4 phi 14 is required at the top. This may go to here and this may go to here. Okay, however, the moment was maximum only at the support and it is going up to 0 at the support, right? So after some dimension, the reinforcement that was extended from the midspan may not continue. This is a possibility. Okay, mostly we may provide for simplicity from one end to the other side. Okay, however, some engineers may, to be economical, may cut some of the reinforcement or may bend it upward and do it at the top. Okay, so for such condition, the reinforcement in the tension zone at the bottom here may not continue fully to the other end. Okay, may not. Okay, so for this assume 50% of the midspan reinforcement is extended. This is just roughly estimation. Okay, you may take 100, you may take 75, whatever. Okay, but it's not good that you use the 100%. Okay, as minimum as half is enough. Okay, now this divided by this gives me 0.00838. Whereas here CP, sigma CP, it is stress induced by the pre-stressing force. So here, since we don't have any pre-stressing force here given, so it is 0. So for this, we will only take the remaining part. So here it's good that you may take a percentage that is about half of the midspan reinforcement. Okay, because it's simply supported. Okay. Now this ratio gives me this divided by this. I will get 0.00838. So you have to check, make sure that it is less than 0.02. So this is the maximum. Okay, the maximum ratio. Now K1 is given here and other factors. Okay, for the V minimum here I have this one. Then finally, if I substitute these values here, I will get this much with the first formula. And with the second formula, I have this much. So always VRDC will be the maximum of these two results. So for sure, it is 74.425. Now, this is for sure less than the VED. So we need to calculate the stirrups. Okay, we need to continue with the calculations. Now, let's continue to calculate the VRD max at 22, our assumption. So at 22 degrees, these are alpha CC for non-pressurized structure. You have to take 1. BW is the width of the beam. Z is 0.9 D. FCD is already calculated. So theta is 22. All these things are calculated. Now VRD max is substituted here. Then finally you get a result of 322.83. Now you have to check that it is greater than this. So now this is verified. Okay. Another is you have to check that it is greater than the support shear. The support shear is 213 as we calculated previously. So again, this is greater than this one. Even if you take the shear at the support, at the center of the support, 225, it is greater than, it is less than this one. So VRD max is safe, and we have now verified that it is safe all along the span of the beam. Now, Let's continue. So everything is okay. Let's go and calculate the shear reinforcement. The shear reinforcement is calculated with this formula easily. Now we need to calculate this part. So this part will be VRDS divided by Z divided by this, okay? So I have to divide this both sides by this part. Now from this, ASW by S will be this one, the shear reinforcement of the web, okay? Now with this cot 22 degrees, I have to calculate this ratio. Now VRDS will be equated to VED, okay? VED directly, then divide this by this, and finally we have 0.516. This is millimeter square per millimeter. This is millimeter square per millimeter. Now once you decide this, then you can calculate this one, okay? Easy. Now with this is our ratio. With this ratio that we have here, check the minimum reinforcement requirement. You can check this minimum reinforcement with this ratio. This is rho equals this by this divided by this. This must be greater than or equal to this. So at minimum, rho will be equal to rho minimum, okay? At minimum. So at minimum, let me calculate this one and take this and equate it with this one to calculate how much ASW by S is required. Now let me deal with this one. To deal with this one, let's substitute this FCK and FYK, everything 0.001. Now this will be minimum if this will be minimum, okay? Now this minimum ASW by S, the minimum ASW by S is found by making this equal to rho minimum. Now this means ASW by S is calculated if I substitute this times this divided by 1, okay? This will be equal to rho times BW times sine of alpha, where alpha is the angle of the stirrup with the longitudinal axis of the beam. Stirrups will be vertical, longitudinal axis of the beam will be horizontal. So sine 90 will be 1. So here I have this much 0.3 ASW by S minimum. Now this minimum is less than the one we have calculated here. So I can continue with this one. So this is the minimum requirement. Now let me check the spacing. For the spacing, let me calculate how much spacing is required for this ratio. Assume 2 legs. What does it mean? 2 legs means these vertical legs that you can see here. So sometimes you may assume if the spacing becomes very close, maybe 4 cent, 2 cent, 3 cent, and you want some adequate space, then you need to increase the legs of the element. For example, you may make it 3 legs like this, maybe 4 legs like this, okay? Now, assuming 2 legs, ASW will be how much area of these bars are there. Now I have 2 legs, right? So there will be 2 pieces of phi 8, right? Where each phi 8 bar will have this much area, pi 8 square over 4. So this is one area of this bar. So I have 2 legs, so I have to multiply it by 2. If I have 3 legs, this part will be 3. Now ASW by S equals 0. This, right? 0.516. Now I know this one. I said 2 legs, this one is noun. So S can be calculated by bringing S to here and this bringing to here. So this one will be ASW by this one. So I have 194.73. So I will take 190 mm. Now let me check the spacing requirement. As per the code, it says the S maximum must be at least at max 0.75 D, where D is calculated to be 450. Alpha means what? The angle of the stirrup with the longitudinal line, okay? So this is 90, cot 90 equals what? Cot 90 means cos of 90 divided by sine of 90, so it's 0. So this will be 337. So which is greater than this one. So the maximum is this one, where I have 190. So my 190 is adequate one, okay? So I will take 190. So phi 8, 2 legged, center to center, 190 mm. Now I will go to the final step, that is the detailing. In the detailing, I have the bottom bar and the top bar. What was the bottom bar? The bottom bar was calculated to be 5 pieces of phi 24 reinforcement. And the top bar will be 4 pieces of 514 at the top, and the stirrups was 58 at 190 around the support, but around the midspan, since the shear is almost zero or minimum, we need to provide a larger spacing here because the shear is very small here. Okay, now let me show you the detail. This is it. So 4 pieces of 514, then again 5 pieces of 524 with this kind of length here, bar cutting like this, and the stirrups is like this. Now we don't know what is up to what length this 190 will continue. Sometimes professionally we may provide L/4. This may be true so many times, but mostly it's better that you check it with the calculations. How do you calculate it? I will show you. Okay, now this is the spacing that I get for the mid part. For the central part, the end parts will be 58 two-legged center to center. This I will show you the section here. So this is the two-legged stirrups. This is 58 center to center like this. This is section YY. Okay, however, your question may be, okay, I was asked this number of times, what is this location? How do you determine this location in calculation? Okay, let me show you how you do it.